ROSILA. I'm Shahrum.
Reinforcement learning about. It is the interaction between the environment and the learning agent that is collecting more rewards obtained, which is the agent improve its environment knowledge to choose or perform the next action. The objective of the studies are to demonstrate the simpler architecture that can explore and memorize very large environment using target-driven visual navigation. Secondly, navigating through unstructured environment is a basic capability of intelligent creatures, and the long-range navigation is a complex cognitive task that relies on developing an internal representation of space. Okay, the next is the input of the study in this experiment, which is they are using a number of large regions that taken in New York, Paris and London, which contains between 7,000 and 65,000 nodes. They are also using the street view regions that have a mean node spacing of 10 meter that will be covering a range up to 5 kilometers away. The problem that encouraged them to involve in the study are large-scale visual navigation based on real-world. Image is the main problem that cannot effectively address a challenging task. They also because many reinforcement learning is only based for navigation that rely on simulators, but cannot be visual, simple and unrealistic. And the last one, they have a problem to navigate in a series of random locations in a city. They expect the outcome is to present a new reinforcement learning challenge that features real-world visual world navigation through city-scale environment, and to propose a dual pathway agent architecture that can navigate within the city-scale environment.
Okay, thank you, AZWANIS. I will continue our presentation on the method. The usual reinforcement learning objectives is to find the policy that maximizes the expected return as the sum of discounted rewards starting from the state has 0 with discount lambda. But in this paper, they're using the Markov decision process that not just only to find the policy that expected return from a state, but also depend on the series of sample code. They hypothesize the career task should benefit from two types of learning, general and local specific. A navigating agent not only needs an internal representation that is general to support a cognitive such as a scene understanding, but also need to organize and remember the features and structure that are unique to a place. Therefore, to support both types of learning, they focus on neural architecture with multiple pathways. The policy and value function are both parameterized by a neural network which share all layers except the final linear output. The agent operator on raw pixel image which are passed through a convolutional network. A long short-term memory, LSTM, receives the output of the convolutional encoder as well as the past reward and previous action. The three different architectures are as shown in the slide. The baseline goal nav architecture has a convolutional encoder and policy LSTM. The key difference from the canonical A3C agent is that the goal description input to the policy LSTM. The CityNav combined the previous architecture with an additional LSTM called the goal LSTM, which receives visual feature as well as the goal description. The CityNav agent also adds an auxiliary heading prediction task on the output of the goal LSTM. Multi-CityNav architecture extends the CityNav agent to learn in a different city. The remit of the goal LSTM is to encode and encapsulate local specific features and topology such that multiple pathways may be added, one per city or region. Moreover, after training on numbers of city, they demonstrate that the convolutional encoder and the policy LSTM become general enough that only a new goal LSTM need to be trained for new city. Curriculum learning gradually increased the complexity of the learning task by presenting progressively more difficult examples to the learning algorithm. They use a curriculum to help the agent learn to find increasingly distant destination. They start by sampling each new goal to within 500 meters of the agent position in the phase 1. Then in the phase 2, they progressively grow the maximum range of the allowed destination to cover the full graph, 3.5 kilometer in the smaller New York area or 5 kilometer for central London or Paris. In this paper, enhancement that be done in this paper is provide extra gradient and relevant information to speed up the learning process by using auxiliary tasks. By using the heading prediction, it can help to navigate in the geometry environment which give the architecture and implementation detail. Thank you.
Bismillahirrahmanirrahim. Now it's my turn to present on result. Result is the performance of proposed architecture on the courier task in large city. The experiment was replicated for 5 random seats and plot the mean rewards NSD and y-axis, and X is the learning step. For the first graph here, we can say here that CityNav gave a best performance hitting the courier task prediction and also better and stable compared to GoalNav. For the graph B here, CityNav agent in London gave the Oracle performance, and the heuristic agent, a curriculum, is used in phase 1 and phase 2. For the result effect of reward shaping here, we prefer curriculum learning to reward shaping here. It is because the former approach keeps agent training consistent with its experience and test time, and also reduce the risk of learning degenerate strategies. For the second result is generalization capabilities on a head-out set of goals. It tests CityNav agent's ability to exploit local linearity to handle unseen goals location. From table give here, increased size of grid size, medium to coarse, the reward also decreased. This means the increased size drop the performance of the CityNav to see the unseen goal location. For third is a transfer in multi-city experiment. Figures show the performance using 3 different training regimes, which is this one for the only target city, this one in multi-city, this one multi-city, with the rest of architecture frozen. It has a mechanism to make transfer to new city. Its effectiveness increased with number of region network is trained, and if set of environment is larger, the transfer also success. The agent is outperformed the baseline of the navigation when the learning performance of agent is lower. The last result is transfer learning performance. The performance in transfer learning that capable to transfer in larger set of environment. As we can see here, as increased number of goal rewards and is also increased with the number of cities. So this one is parallel here. Joint multi-city training and transfer learning performance of variants of the multi-city nav agent is possible. Isolating the local LSTM as a bottleneck can reduce the overfitting of the convolutional features and enforce more general interface to the policy of LSTM. As a conclusion, the prediction of measurements, which is the goal, is designed using proximity to local landmarks. This is to overcome the problem of navigations that only rely on simulators, but the visual is simple and unrealistic. Problem is in navigate in a series of random locations is solved, where the rewards that the agent gets upon reaching a goal is proportional to the shortest path. The next goal is randomly chosen and be input if the goal is within 100 meters, approximately 1 city block away. Navigation is an important cognitive task that enables humans and animals to traverse a complex world without maps. We make some references to deep know about this article and what is to know more about this study.